Hello again, everybody. This is Mr. Church. I really shouldn't say Mr. Church. I mean, who else could it be? But anyways, I just feel like I need to say that. Today we're going to dive into irrational numbers. Okay, we've learned a little bit of rational numbers, changing decimals into fractions and vice versa. And now we're going to look at the other side of the spectrum. This one's a little trickier, but it's a very common type of problem you might see, or it's involved in a lot of problems you might see on the check-in or an EOG. These do arise quite a bit in real life with calculations because not everything is a nice, neat integer or a number that's, predictable, which, repeating decimals, for example, from yesterday were, pretty predictable. They repeat, right? But what happens when we have decimals that don't repeat and they do go on forever? And you guys are very aware of one very special type of irrational number that never repeats and never ends. I'm sure somebody may have just said it. But we're going to dive into other numbers that are just like that one. And if you don't know what that number is, we'll talk about it again here in just a second. So today you'll leave understanding, hopefully, um, the meaning of irrational. So there is a mistake here in our notes. You can go ahead and fix this where it says explain the meaning of rational numbers. That should be irrational. So we'll fix it real quick. Just put the word irrational above that. Because we already know what a rational number is. Rational numbers can be expressed as fractions, as a over b. That's the way we agreed we'd do it because most of you understand what a fraction is. Irrational numbers, though, are a little different. You should be able to write fractions and mixed numbers as decimals or write repeating. This looks a lot like yesterday's. I think this whole thing's just flat out wrong because that doesn't seem like the thing that we should be learning. So you know what? I should probably hire a better proofreader or editor, which is me. So I'm very bad at this. So actually, all that's wrong. Today, your goal is to learn what an irrational number is and classify real numbers as either rational or irrational, approximate irrational numbers, and then solve real life problems with involving irrational numbers. So all this is just a complete mess, but we're going to roll with it. That's fine. You can laugh at me. Just goes to show you that even me, I make mistakes, and I've done this for years. So, but we're going to keep going, and you guys will still learn what you need to today, and we'll just figure that out as we go. So first of all, we're going to dive into what an irrational number is. No exploration today, like yesterday. No lengthy dive into calculating or anything. We're just going to go right into vocab. So what is an irrational number? If a rational number can be expressed as a over b, then what is an irrational number? Well, it's simply a number that is not rational. Okay, it can't be written as a fraction or expressed as a number a over another number b. I don't even know. See, this has got typos. I don't understand. Scratch out that D. Evidently, when I made this, it must have been really late. So an irrational number cannot be written as A over B, where A and B are integers. Again, the easiest way to probably phrase it is irrational numbers cannot be written as fractions, and where B is not equal to 0. It's just not possible. Okay. So what are some types of irrational numbers? Well, there's not a lot, but the most common ones you guys have seen so far are, well, the one that I mentioned earlier that you guys have probably heard of is the number pi. Pi is probably the most common and popular irrational numbers that you guys know, right? Because we have a Greek symbol, a Greek letter really, to represent that number. Why do we need a Greek letter to represent the number pi? Because pi goes on forever and it never repeats. All right, if it repeated, we could write it as a fraction. We learned that yesterday. Okay, we can write repeating decimals as fractions. But this one never ends, it never repeats. In fact, some very intelligent person figured that out before the modern calculator was invented. I don't know how they did it, but they did. So besides pi, though, what are some other types of irrational numbers? Well, we've actually seen some recently with square roots, right? When we take the square root of a number that's not a perfect square, we get a number, a decimal that goes on forever and ever. Now, yesterday I passed out in class a handout, and I'm going to scroll down here to it. And if you did not get it, there should be some copies maybe on my front desk somewhere, maybe on my back desk, and you can just raise your hand. But most of you got a copy. Grab that real quick. Just open your binder. You don't have to get it out. but just have it there available. I'm going to tell you what this sheet means. Now this is, and I described it yesterday, or the other day when I was there, Tuesday, that this replaces your calculator when it comes to a lot of these types of problems. You can't have the calculator on part of the EOG, and this right here really takes its place. If you understand this list and part of what's in this list, you will be a lot more successful on these types of problems on your check-in and on your EOG. You do not have to memorize this entire list, but I am going to go ahead, and I did this for clientele already. I'm going to mark where you should go, how far you should go. Now, I've got good news and bad news, okay? The bad news, we'll start there first, is you really need to memorize the middle column. That would be this one right here, okay? You need to memorize that entire thing. And honestly, you're not going to sit down and do that, right? Nobody's going to do that. But the more we use it, the more you'll start to memorize it. On the third column, these over here, you really just need to get down to about right there. 10 cubed equals 1,000. But what exactly is this? Like, what are you memorizing? Well, let's go through the columns. This is a list of the perfect squares and cubes. All right, so if you look at the first column, we have numbers from 1 all the way down to 20. Okay. In the middle column, you have the numbers from the first column, okay, but we're squaring these numbers. Notice it's 1 squared, 2 squared, 3 squared, 4 squared, okay? And as a result of that, we get the list of perfect squares, the numbers that, those special numbers that when you take their square root, you get a nice integer value. For example, those numbers are 1, because what's the square root of 1? What number times itself is 1? Oh, it's 1, okay? 4 is the next perfect square. What is the square root of 4? What number times itself is 4? Oh, it's 2. The next perfect square is 9. Okay, what's the square root of 9? 3. What's the square root of 16? 4. The square root of 25 is 5. Okay, look at these numbers. Notice not every number is a perfect square. There's a lot of numbers that we've already left off this list that are not in this middle column. Okay, for example, from 1 to 4, we don't see 2 in the list or 3. These are not perfect squares. Do yourself a favor, grab your calculator and type in the square root of 2. Okay? And what do you get? You get some awful looking decimal like 1.414213562. And guess what? That decimal goes on forever and ever, and it never repeats. It's an example of an irrational number. Just like pi, that number never ends, never repeats. Same thing for the square root of 3. All right? So what we have here are a list of the special numbers, the perfect squares. And you should really memorize all the way down to 400 at minimum, all the way down. And the more you use this list, the better you'll get at that. So you really don't have to sit at home and do that. Nobody's going to do that anyways. Over here in the third column, though, we have our perfect cubes. Okay? So think about this. 1 is our first perfect cube. Okay? What number times itself again is 1? Well, the number in the first column, 1. 1 is the cube root of 1. What about 8? Why is 8 a perfect cube? What number times itself again is 8? Well, the number over here in the first column, 2. 2 cubed is 8. It's right here as well. Okay. 27 is the next perfect cube. What number times itself is 27? 3. And as you go down this list, you'll see the other perfect cubes all the way to the 20th perfect cube, but you just need to go down to the 10th perfect cube, which is right here. That is 1,000. Okay. There's a lot of numbers that are not listed here. Okay. So for example, notice how 1 and 8 are the first 2 perfect cubes. Okay. But 4 is not listed. It's not one of the numbers we highlighted. What is the cube root of 4? Now you're thinking, oh, it's 2. No. The square root of 4 is 2. And that's great. 4 is a perfect square. But is 4 a perfect cube? Take your calculator, go to Math, pick option 4. Okay. and let us type 4 after that. So math 4, find the cube root of 4. The cube root of 4 is 1.587405 and it ends on the calculator, but it actually keeps going forever and ever and ever. And it never repeats. Look at this, none of that repeats. And it's never going to. So that's another example of an irrational number. Now I say all that to help you understand what this list means, but also to draw our attention back to the types of irrational numbers. So basically, pi is a great example, okay? But anytime you have like the square root of a non-perfect square, like the square root of 3, the square root of, 5. You could even say the negative square root. You're like, oh, you can't take the square root of a negative. We're not taking the square root of a negative. Notice how the negative is on the outside of the radical. So the negative square root of 10, okay? So right here, we could say, well, anytime you take the square root of non-perfect squares, numbers that are not perfect squares, you're going to get those types of irrational numbers, those decimals that never end and they never repeat. Okay. Likewise, if you take the cube root of non-perfect cubes, like the cube root of 4, that was one of the ones we looked at. If you take the cube root of um, 17, the cube root of 100. 100, 100 is a good number, right? Well, go down here in our list. Is 100 one of the perfect cubes? Look right here. I don't see a 100. I see 64, and then it goes straight to 125. Well, it's in this list over here. Yeah, it is, because 100 is a perfect square, but it's not a perfect cube. All right, so you got to be careful sometimes when you think about these types of problems. So other types of irrational numbers occur when you take the cube root of non-perfect cubes. Those are your common examples of irrational numbers. So let's write down also what we learned about irrational numbers, and I'm going to change colors to emphasize this real quick. Okay, irrational numbers. And we'll change this a little bit more. Let's make this a little more bold. I want it to really stand out here. How do we do that? Oh, it looks better. Okay, that doesn't look any better. Come on, iPad. Let's try this. There it is. That's a little bit thicker. Irrational numbers. As we saw from our calculator, okay, they never, in decimal form, they never terminate. What's another word for terminate? They never end. Okay, you ever seen Terminator, the movie? When people get terminated, what happens to them? They end, right? And they never repeat. Okay, in decimal form. They never terminate and they never repeat. Very important idea. That's what you need to look for. Okay, and that introduces to us the two sets of real numbers. Okay, the numbers you guys have learned about on all your schooling years are considered real numbers. Okay, and there's two categories. We have our rational numbers over here, rational, and we have irrational. Okay, you won't learn about imaginary numbers to get to high school. Now, how do you make sense of this chart here? Like, what exactly is going on? Well, let's look at the blue side first, irrational numbers. All the possible irrational numbers in the world, in the universe, basically all belong to the same group. It's just the big group of irrational numbers. Okay, that's why there's one blue circle here, and the word irrational is on the inside. It's more complicated when you get to rational numbers, though. Notice how this largest oval is labeled with rational, but within rational numbers, we have these other ovals. We have a special set of numbers that are called integers right here. So I can't trace that with a lick, but that's okay. And then inside of integers, we have another oval, special numbers called whole numbers. And then we have special numbers inside of that that are called natural numbers. And the best way I know to make sense of that kind of chart is with this. You don't have to draw this. I'm going to come in here and maybe make my own little chart. Okay. So let's suppose that we have this oval here. It's probably going to make a circle. Oh no, it made an oval. That's great. Okay. Let's suppose that this oval represents um, every, well, all of North America. We'll just say all of North America. Yeah, let's do that. North America. Get rid of that. Okay, North America. Now, North America is a continent. Does anybody know the three countries that make up North America? The United States, Canada, and Mexico. Hopefully somebody got that, okay? So, anybody who lives in the United States, Canada, or Mexico is North American, okay? Now, this next oval I'm going to draw represents only part of the people who live in North America, not all of them, okay? Because, we have this space out here that's not in the oval, okay? And that represents people who are North American, but they don't belong to this inner oval. So let's suppose that this inner oval represents people who live in the United States. So what kind of people would belong then out here that are North American, but they're not in the United States? Well, that would be people that are Mexican, or you could say people that are Canadian, right? They're North American, but they're not in the United States, so they don't belong in the United States oval. Now think about this, okay? Inside the United States oval, we have a group of people who live, and we'll say, well, this is the people who live in North Carolina. I'm just going to put NC for North Carolina, okay? NC. So if the people in the inner oval are people who live in North Carolina, what kind of people would live out here? They're in the United States oval, but they're not in the North Carolina oval. That'd be people who live in, Tennessee, Virginia, Arizona, California. What is that? What are the initials for California? Let's not pick that then. I don't know. I can't remember. New York. Okay. And then inside of North Carolina, we have another oval. Whoops. Again, you don't have to draw this. We're just watching here. Let's say that this oval right here represents people who live in one of the special counties, the best county in North Carolina, and that would be Ashe County. Okay, this would be Ashe. All right, so then who would be the people who live in the North Carolina oval, but they're not in the Ashe County oval? Well, that would be people who live in all the other counties that aren't as good, right? And like, think about the worst counties, like Watauga County. I'm just kidding. We just don't like playing Watauga in sports, right? And then we have like Avery County and other counties. My wife's from Watauga County, so I better not say too much. All right, so here, let's say, raise your hand if you live in Ashe County. Go ahead. Yeah, most of you live in Ashe County. There's the exception sometimes where kids actually don't live in Ashe County, but let's suppose here you are. Ta-da! There you are. You are an Ashe Countyan, right? Well, let's suppose that this person inside the Ashe County circle says, "Haha, well, I'm actually an American." Well, is it okay for them to say that if they're in the Ashe Oval? Well, yeah, because anybody in the Ashe Oval is also inside of the United States Oval, right? If you're in this oval right here, you're inside of the larger United States Oval. So if you live in Ashe County, you can also say, not only am I an Ashe Countyan, I am an American. You could also say, because the Ashe County circle or oval is inside North Carolina oval, that you're North Carolinian. And you can say that you're North American. So all those names can apply. If you live in Ashe County, you can say that you're an Ashe Countyan. Okay, if that's how you say it. You are a North Carolinian. You are an American. and you are a North American. I'm just scribbling this because you just heard me say it. So all those names can apply to the same person at the same time. Now, if you kind of understand that oval and how they are nested or they fit inside each other, then you can start to understand what this oval up here means. Okay, so start from the inside. The very inside oval is what we call natural numbers. Numbers like 1, 2, 3. And based on that, we would assume 4, 5, 6, 7, 8, on and on and on and on and on. It doesn't end. Okay. So that means that positive numbers that you could count, like on your hand or with rocks or with beads or whatever, livestock. I guess that's where you could say the natural name comes from. Numbers that occur in everyday life. And a lot of times in normal everyday life, we count things, right? What that doesn't include, though, is decimals. It's hard to count decimals or fractions, okay, because they don't arrive. We don't deal with decimals and fractions in real life in ways that are usually counting now, but we do that sometimes, but it's not as natural to count those. It's really not the best way to say that, but it just doesn't include decimals and fractions. Natural numbers are 1, 2, 3, 4, 5, 6, on and on and on. Notice how zero, though, is not in this oval. Zero doesn't show up until the next oval when we get to whole numbers. Okay, so what are whole numbers? Well, whole numbers includes um, all of these numbers, the natural numbers, and then anything that's inside the whole number oval, which is just zero. Okay, so the only difference between natural numbers and whole numbers is zero. Zero is not a natural number, and then all the natural numbers are considered whole. And then outside of that oval, we have our next oval, which is the integer oval. So what do integers include? Well, integers include all the natural numbers and all the whole numbers because they're inside of the large integer oval. Okay, so it includes 0. Integers include 1, 2, and 3, but they also include these types of numbers, -1, -2, and -3. Okay, so just to make sure if you like really understanding this is think about the number 2 here. If I can get this to work. The number 2. Notice how it's inside the natural numbers oval. So 2 is a natural number, but it's also in the whole number oval. So it's a whole number. But it's also in the integers oval, so it's an integer. And it also belongs to the largest oval over here, which is the rational numbers oval. So it's a rational number. So just little old measly 2 has all those names. Just like you, who live in Ashe County, you're an Ashe Countian, a North Carolinian, an American, and a North American all at the same time. 2 is a natural number, it's a whole number, it's an integer, and it's a rational number all at the same time. Okay. What about -2 though? What are the names that apply to it? Is -2 in the natural numbers oval? No. Is it in the whole numbers oval? No, it is not. Okay, let me clean this up a little bit. -2 is only inside of the integer oval. So -2 is an integer, and it's inside of the larger rational numbers oval. So it's a rational number. So there's a difference just based off of whether it's positive or negative. Okay. Notice, for example, -2/3 over here. Let me clean this up again. -2/3 in this large oval. The only oval over here that -2/3 is in is the rational numbers oval. It's not in the natural numbers oval, the whole number oval, or the integer oval. So the only name that really applies to -2/3 is it's a rational number. Okay, so that's how this works. And that's what you need to be able to use in order to classify numbers. Classify means to put into categories or to separate into groups. All right, so let's try that down here on example 1. Classifying real numbers. Let's look at the square root of 12. The square root of 12. Well, is 12 a perfect square? If we go down here to our list, is 12 in this middle column? It should be like right in here, right? It's not there though. So what does that tell you? Without even picking up your calculator, if you were to take the square root of 12, would you get a nice number, or would you get one of those long decimals that never ends and never repeats? Yeah, you'd get one of those decimals that never ends and never repeats. So when you get that, then what kind of number is that? Well, that sounds like a type of irrational number, right? When you take the square root of a number that's not a perfect square. So without even grabbing our calculator, we can say, oh, I know that. Well, I know what happens when you take the square root of 12. You get an irrational number. I better size this back down. So we're going to say it's irrational. An irrational number. Never ends and never repeats. And if you're curious, go ahead and type in the square root of 12 and see what you get. And y'all say, I told you so. See? Told you so. All right, let's go to negative 0.25 repeating. Now, there's a repeating sign, so we have a 2 and a 5. So we learned earlier, really yesterday, I guess, that if you have a repeating decimal, we can write it. Just take the digits that repeat and put them in the numerator, and then put a 9 in the denominator for each digit that repeats. So since we have 2 digits repeating, we're going to have negative 25 over 99. So what kind of number is that then? Well, it's a fraction, right? So let's look up here in our real numbers diagram. Where do we see fractions? Do we see fractions over here in the irrational numbers? No. Remember, you can't write irrational numbers as fractions. So fractions don't belong over there. Fractions belong over here. But where do we start seeing fractions? Where's the only place we see them? Well, we see them over here in this biggest oval of all, which is the rational numbers oval. Okay, which tells me that fractions, like the one we have, are considered rational numbers, but nothing else. They're not in the integers oval, they're not in the whole oval, they're not in the natural oval. So this is simply just a rational number. Negative square root of 9. Negative square root of 9. Well, that's square root of 9. 9 is a perfect square. So that would be negative 3. So where do we see numbers like negative 3 up here? Oh, well, there's negative 3 right there. What oval is it in? It's in the integer oval. And because of that, it's also in the rational numbers oval. So we can say that negative 3 is an integer and a rational number. Integer and a rational number. Down here, the cube root of 15. Now you might be tempted to grab your calculator, but remember we're replacing our calculator with our list here. So look at our cubes, perfect cubes. Is 15 a perfect cube? I'd expect it to be after 8 and before 27, and it's not there. So we already know what's going to happen when we take the cube root of 15. We're going to get some long decimal that never ends and never repeats. And again, that is the definition of an irrational number. An irrational number. And lastly, we have pi, and we already know that that's irrational. That's one of our most popular irrational numbers. All right. So, yeah, not too shabby. I want you to go ahead and we're going to stop here for today. That's enough notes. So today is, what is it, Thursday? So I want you guys to stop. You're going to work on an IXL skill or two. You may get done early. I may just do one IXL skill today. Let you get caught up on anything else you need to. Again, if you get done, okay, you can just read or draw quietly. And then I'm not going to make a separate video like I did for my Math 1 group. So if the substitute can just pause this, and then tomorrow you guys will watch this same video, but you're going to start it back here. Okay, and I can't tell how much time has passed already, but just know to tell the sub, if it's not the same person, that you're going to start back here tomorrow with example 2, and you've got that in your notes, okay? So I'm going to be quiet for a few seconds to kind of simulate pausing it, and then tomorrow you'll start back up and we'll just be right here, okay? All right, guys, so today should be Friday. Welcome back. And we're going to pick back up with examples 2 and 3. And then after this, give you guys some time to work. And hopefully you can go home and say you got everything done that Mr. Church wanted you to do. So yesterday we learned about classifying numbers, irrational and rational numbers, and what an irrational number is. Today we're going to approximate irrational numbers, and we're going to go back to using this list again from yesterday. Now I'm going to clean it up a little bit since we marked on it, or I marked on mine, but we're going to come back to that and get that out again so we can use it. So how do we approximate an irrational number? What does approximate even mean? That means we're kind of guessing um, or estimating, you could say. Might want to write that down. The value of an irrational number without a calculator. Okay, so they want us to approximate here the square root of 71 to the nearest integer. Now remember, integers are numbers like -4, -3, -2, -1, 0, 1, 2, 3, 4, dot, 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 keeps going on. So they want us to basically round it to the nearest whole number or the opposite of a whole number, a negative number, okay? And then they want us to do it to the nearest tenth, and that means one place past the decimal. So I'm going to show you how to do that, but again, we're not going to use the calculator. We can check with the calculator, but we're not going to use it. So let's start with the square root of 71. Let's first start with the obvious. Is 71 a perfect square? Is it easy to find the square root of 71? Let's go down here to our center column and see if 71 is one of these perfect squares. So we're just going to go down through here, and I see 64 is a perfect square and 81, but 71 would be in here between those two, right? So 71 is not a perfect square. It's between the perfect square of 64 and 81. And that's a very important idea, because if I want to estimate what the square root of 71 is, I first need to realize that, well, 71 itself is between 64 and 81, right? So then it makes sense that the square root of 71 will be between the square roots of, or be between the square roots of 64 and 81. Now, if you're probably wondering, like, well, why did you pick 64 and 81? Well, because they're two of those special numbers that are perfect squares, and 71 is between them. Okay, so that means that the square root of 71 is going to be bigger than the square root of 64, but it's going to be smaller than the square root of 81. So let's start with what we know. You often hear me say that. What is the square root of 64? Well, we'll stick with the positive version today. It's 8, right? And what is the square root of 81? 9. So the square root of 71 must be between 8 and 9. So which one is it closer to? Well, let me ask you guys. Which number is 71 closer to? Is 71 closer to 64, or is it closer to 81? Well, 71 is only 8, no, 7, 7 away from 64, but it's 10 away from 81. So then the square root of 71 is probably closer to the square root of 64. So I would say that the square root of 71 is about 8. And that is our integer estimate. To the nearest integer, it's about 8. But how do we get it to one place past the decimal? We want 8 point something. How do we get that extra number? Well, let's go back to what we know about 71. 71 is a little bit closer to 64 than it is 81, right? Okay, the distance here is only a distance of 7. The distance here is a distance of 10. So 71 is definitely closer to 64. But it's not super close to 64, right? It's 7 away, okay? And it's 10 away from 81. Now, what would you guess the square root of 71 would be if it was an equal distance away from both numbers? Let's suppose that this number here Let's say that it was 8 and 8, that it's 8 away from both. If 71 is smack dab in the middle of 64 and 81, then wouldn't it make sense that the square root is also smack dab in the middle? Yeah, so then you'd guess 8.5, right? Because that would be halfway between 8 and 9. But 71 isn't smack dab in between 64 and 81, going back to what we said a second ago. It's 7 away from 64 and 10 away from 81. So that's going to push the square root a little bit closer to 8. Not a lot closer, but a little bit closer. So instead of 8.5 over here, it's going to push it a little bit closer to 8. So what do you think? Maybe 8.4? Maybe if you want to go a little bit farther, 8.3-ish. But I think I like 8.4. Now, I told you we would check with our calculator. So come over here and hit on your calculator, do the square root of 71. And what do you get? Aha, you get 8.426. 8.426, and it keeps going on and on and on and on. All right. Now, I want you guys to try another one here. You don't have to write this one down. I'll just write it over here. What about if we wanted to approximate the negative square root of 13? The negative square root of 13. Let's go back down here to our list. Is 13 a perfect square? Well, 9 is, and 16 is. 13 would be between 9 and 16, right? So 13 is not a perfect square. So when we take the square root of it, it's not going to be pretty. The negative on the outside, we're just going to remember that it's there, but we're not going to mess with it just yet. Just think about 13. 13. 13 is between the perfect squares of 9 and 16. Right? So that means the square root of 13 should be between the square roots of 9 and 16. Why did we pick 9 and 16? Because we know the square roots. They're easy to find. Like the square root of 9 is 3. And the square root of 16 is 4. So that means that the square root of 13 is between these two numbers. So what do you think would be a good guess for the square root of 13? Well, is 13 smack dab in the middle of like 9 and 16? I don't think so. Right? If we go back to just looking at 13 and 9 and 16, 13 is 4 away from 9, but only 3 away from 16. So that means that the square root of 13 is going to be a little bit closer to 4. Oh, that's a terrible looking piece of whatever that is, type of pencil. It's going to be a little bit closer to 4. So it's not going to be 3.5. It's going to be a little bit closer, like 3.6. So I'm going to say it's 3.6. Okay, however, remember there's a negative on the outside, so we're going to estimate negative 3.6. Let's try that. Go on your calculator and type in negative sign, and then hit square root of 13. And we get, so looky there, negative 3.60555. So, and that was without a calculator. We were able to get one place past the decimal. So guys, that's how you use your sheet down here to approximate the value of these square roots. And it also works for cube roots. So you'll have some cube root problems, like the cube root of 25 should be really close to the cube root of 27. Well, the cube root of 27 is 3. So the cube root of 25 must be close to 3, like 2.8, 2.9, maybe 2.7, somewhere in there. Example 3, last one, and we're done. Compare any rational numbers. Which one's greater? The square root of 35 or the cube root of 80? Well, let's start with the square root of 35. Is 35 a perfect square? No, it is not. But it would be between these two perfect squares. 35 would be between those two. In fact, 35 is extremely close to 36. So we can probably with confidence say, well, the square root of 35 is about the square root of 36. And we know the square root of 36, right? It's 6. So we could say the square root of 35 is about 6. What would you guess, though? If it's not exactly 6, it'd be a little bit less. So what do you think? About 5.9? Without a calculator, don't type it in. Let's just go with 5.9. So that's reasonable, right? So that was quick. But what about the cube root of 80? Is 80 a perfect cube? Let's go down here. Is 80 in my perfect cube list? No, it's not. I have 64 and I have 125, and then 80 would be somewhere between those. Okay, so, well, if you think about 80 here, how far is 80 from 64? That would be 16, right? And then from 80 to 125 would be 45. So 80 is a lot closer to 64. So then the cube root of 80 should be really close to the cube root of 64. The cube root of 64 was 4. 4 times 4 times 4, 64. So I imagine that the cube root of 80 is really close to that, like maybe 4.1, 4.2, something like that. So let's just go with about 4.2. Now grab your calculator. Let's see if this is correct. Based off what I see right here, I would say the cube root of 80 is less than. So we would say the square root of 35 is greater than the cube root of 80. You're like, what? Wait a second. Where did that sign come from? Well, that's a sign you learned back in 7th grade in elementary school, right? It means greater than. Type in on your calculator the square root of 35. How close were we? We said 5.9. Look at that. 5.916. Now let's find the cube root of 80. Go to math, pick 4, type in 80. You got 4.3. I guess 4.2. That was close, you know. But our answer still stands. The square root of 35 is greater than the cube root of 80. How do we know that? Well, we guessed that the cube root of 35 was 5.9, and 5.9 is greater than what I guessed for the cube root of 80, even though the cube root of 80 is really 4.3-ish. And again, notice how I'm relying on this chart down here. Super important chart, okay? Guys, that's it for today. Again, you're going to have some IXLs to work on. Those codes can be written on the board. Once you get done with those, you can read or draw quietly. If you don't get done, we'll try to pick up next week. Try to get done if you can. Don't distract other people, and have a great rest of your day.